Hi, everyone. This is joint work with Willie Neiswanger, who is a postdoc at Stanford University. Our work is on uncertainty quantification using martingales for misspecified Gaussian processes. So Gaussian processes are often synonymous with uncertainty quantification, but they can be very brittle due to misspecification, especially of the prior. The performance may not degrade gracefully if the prior is inaccurate. In my view, priors are always misspecified. We make them up, but they can be useful regularizers. There are frequentist approaches to uncertainty quantification that are underexplored, that are robust to prior misspecification, but they use so-called working priors. And these are also robust to optional stopping and continuation of experiments. These techniques use what are called confidence sequences, which are based on super martingales. Confidence sequences are usually efficient, but for Gaussian processes, there are some numerical difficulties I'll describe briefly. So there's plenty of research to be done to build on this work of ours. As a recap, a Gaussian process is a non-parametric prior distribution over functions. So a random draw from a GP yields a function, and it's specified using a kernel kappa that describes the covariance between function values across the space. So here's an example. These are functions drawn from a particular GP prior that I'm going to call prior A. This is a Gaussian process, a Gaussian prior with a particular length scale and signal variance. One example where GPs are very useful are derivative-free global optimization. Here there's some unknown function f star and there's some unknown minimizer x star that we are trying to find by querying the function at different points, obtaining its values. When at time t we query at point xt and we receive yt, which is approximately f star of xt. Now in Bayesian optimization, they often assume that f star was a random draw from a Gaussian process with a particular kernel. Why do they assume this? I think computational convenience is one important point. There's been decades of work to build upon. But usually nature is not so kind as to draw f star from our made up prior. Let's have a quick look at what happens to GP posteriors for Bayesian optimization or Gaussian process regression when the prior is actually accurate. So in this example, the blue function f star is drawn from a Gaussian process B, and then it's just fixed. The gray band is actually going to be the Gaussian process posterior band correctly specified using prior B. The pink dots are observations which are corrupted by a small amount of Gaussian noise. So what you see over here is an increasing number of samples. And if you look at the bottom right of the plot, you'll see that most of the pink dots, which is most of the queries, are near the minimum of the function. And so in this case, the blue curve is pretty much well covered by the posterior band, which is the gray part. And there's very low uncertainty near the minimum, and it has correctly identified the minimum. So this is a good case when the prior was accurately specified. Now let's look at what happens to the posteriors when the prior is inaccurately specified. Okay, so these are functions I've showed you from GP prior A, and these are typical functions from a slightly different Gaussian process prior B. Okay, the kernel is the same, just change the length scale and the sigma parameter. So what we're going to do in this experiment is we'll draw f star from B and we'll fix it, but we'll use Gaussian process or Bayesian optimization using informed by prior A. Okay, and already in this case, nature is being relatively kind to us. It does not need to draw f star from a Gaussian process at all. And if it does draw it from a GP, why would it use our kernel and hyperparameters? So this is still a relatively favorable for Gaussian processes simulation. So the active case is one in which the point is queried by minimizing the lower confidence bound. This is a standard LCB algorithm, or UCB if you were maximizing. And what you'll see is that already with a few points, the posterior, the gray band, is completely overconfident about the function and also extremely inaccurate. It does not cover the function at all. And as you get more and more points, remember that the user does not know the blue curve. The user only knows the gray band. And so the user thinks that there's very low uncertainty around the minimum. The minimum has been identified. In this case, it's querying a lot of points in the bottom right graph. It's querying a lot of points near zero. Things look wonderful, but since the blue curve is not known, they don't know that they've completely missed the minimum. And the minimum in this case was around 9.5 or so. There's nothing special about the active case. This happens in the passive case itself, and I'll show you an experiment of that kind. Here, xt is drawn uniformly on minus 10 to 10. Again, the blue function f star is drawn from GPB, and it's just fixed. The gray band is going to be the GP posterior band using prior A. So it's misspecified. The pink dots are the observations, and the brown band is our confidence sequence for F star. What you'll see is that the confidence sequence after just a few points it's extremely wide, and it definitely is not useful at this point. But at the other extreme, the GP posterior is overconfident and completely inaccurate. The interesting difference comes out when you query more points. So what you're seeing is 25 points on the left and about 40 points on the bottom right. Or now what has happened is that the brown curve, the confidence sequence, has shrunk and actually does cover the true function reasonably well. The gray curve, however, continues to remain inaccurate throughout. It does not cover the function anywhere. So it never recovers because of increasing amount of data. And this might seem a little bit surprising to those who are familiar with the Bernstein-von Mises theorem, which says that the posterior should typically be consistent. But again, in the active or the passive case, we saw that the posterior was not consistent. And on the other hand, the confidence sequence, which I'm showing here in the active case, in the bottom right graph, does actually identify the correct minimizer of the function. So here's a cautionary note from Friedman's Wald lecture in 1999, in which he points out that for infinite dimensional models, the Bernstein-von Mises theorem does not hold. And so he points out that Bayesians need to proceed with caution in the infinite dimensional case unless they're convinced of the fine details of their priors. Indeed, the consistency of their estimates and the coverage probabilities of their confidence sets depend on the details of the priors. And this, I think, is an example of what we're seeing on the previous slide, where the prior was reasonable, but the details were slightly wrong, and the posterior seemed to be inconsistent, and whether you're sampling passively or actively, it didn't matter. So what we're going to do instead is construct a confidence sequence for F star. And a confidence sequence is a sequence of confidence sets, Cn, n is the sample size, with a uniform or simultaneous coverage guarantee over all of time. And so the probability statement says the probability that for all n simultaneously from 1 to infinity, the probability that F star is in Cn is at least 1 minus alpha. So this concept was introduced by Robbins along with many collaborators, Darling, Rai, Siegmund, and others in the 60s and 70s. Kind of lost popularity for a few decades, but because of bandit applications has regained popularity. One important implication, if you're able to construct a confidence sequence, is that for any stopping time, for any arbitrary data-dependent stopping time, the probability that F star lies in C tau, which is the confidence set at the stopping time, the probability that there is a miscoverage is at most alpha. So what this means is that you do not have to pre-specify sample size. You can extend or stop experiments adaptively. Confidence sequences are very useful for quantifying uncertainty. So we have a recent work, this is by Steve Howard, John McAuliffe, and Jas Sekon, and myself, in which we derive a variety of time uniform, non-parametric, and non-asymptotic confidence sequences. And we will build on some of those ideas, but some new ideas to develop confidence sequences for F star over here. So broadly speaking, this is the strategy we're going to use. We're going to construct a family of processes, RT of F. It's indexed by F. For every function in the function space, there's a different process RT. T is time, the number of samples that you have collected so far. And this family of processes will be constructed such that just one of them, RT of F star, we don't know which one that is, but RT of F star will be a non-negative super martingale. In fact, in our case, it'll actually be a non-negative martingale. And the initial value, R0 of F, when you don't have any data, for every function F is just going to be a constant, which is 1. So how do we construct it? We have this lemma called the prior-posterior ratio martingale. This is going to be useful in many contexts outside of the one that I've presented as well. So I'll present the lemma more generally. So for any parameter space theta, we are allowed to choose a working prior pi 0 of theta. This does not have to be correctly specified at all. There's no Bayesian assumption over here. It's just a mixture distribution over the space theta. Now, after observing some data from p theta star, which we don't know, we calculate the working posterior pi t of theta. Again, this is over the space theta. Now, we're going to form this process RT of theta for every theta in the space, which is the prior posterior ratio. It's the ratio of pi 0 of theta to pi t of theta. This process is a non-negative martingale only at theta star. So RT of theta star is a non-negative martingale with initial value 1. In our case, the underlying parameter space, it's not a parameter space, but it's going to be the underlying space is going to be script f. The working prior is going to be a Gaussian process prior. The data is coming from some f star. The working posterior is a Gaussian process posterior, and RT of f star is actually a non-negative martingale. We then use Wheel's inequality, which is a time uniform version of Markov's inequality for non-negative supermartingales. So if you remove the exists t sign, this statement is actually just Markov's inequality because it's a non-negative random variable. But because it's a non-negative martingale, you actually get this time uniform property. It's a very powerful theorem. You can invert this to get a confidence sequence for f star. It's a set of all functions for which RT of f is at most 1 over alpha. Now, there are many challenges in implementation because we have to pick this function class script f so that CT is easy to compute. But our idea was to implicitly define script f through a computational procedure. I won't go into detail as to how we come up with this computational procedure, but there are many other problems, for example, in deep nets where we cannot write down script f, but we actually can. It's implicitly defined, and so this is in that flavor. There's a particular parameter which we call the belief parameter, which you can think of like a regularization parameter. We use it as 10 to the power minus 5 in simulations. As gamma goes to 0, we obtain the original confidence sequence, which is very robust, but a bit too wide. And as gamma goes to infinity, we obtain the usual posterior GP band, which is very non-robust, but very short. And so you can think of gamma as how much do we believe in our prior? If we believe a little bit, in this case, 10 to the minus 5, we have some balance between wideness and robustness. There are many other challenges we outline in the paper, which are still open, statistical and computational trade-offs in picking script f. How do we identify gamma in a data-dependent way? How do we adapt all of this to account for hyperparameter tuning? And what if the observation model is itself misspecified? If you're interested in these topics, I encourage you to check out our paper. And I'd once again like to thank my collaborator, Willie, and thank all of you for your attention.